example over here. Will there be change occurring in this?
X.
No, right? Here, if we move up, will the change occur?
At the top, after the top.
Right, but within a delta of this
No,
one?
no.
No, but if I move it this way?
Yeah. Yes.
Yes, right? But in a corner, both ways it will
Both
change.
ways.
Okay, so it's, as you know, the author says, for a corner, we should expect significant change in all directions as we move the small window. Okay. So now let's take a look at the mathematical approach. So Harris corner detector gives a mathematical approach to determining which case holds better, meaning which one is a potential corner. Okay, so here's our function for determining the intensity of change. Okay, so WXY basically is a small window over here. Okay, so in 2 dimensions, think of this will be like a box, is the WXY. Okay, and XI, X plus U, so UV is the variation that we are going to move it by. So U could be 1 pixel, could be 2 pixels as we move it to the right or the left. And so as we move, we compare it with the original, and we do it for all points in the window, and then we sum it over all points. And if this is a high intensity, then it's a corner, otherwise it's not. Okay. What's a good choice for a window? We could use a square window. We could also use a Gaussian, because if you take a look at a Gaussian also is like a square window. Okay, so either one could be chosen. Okay, so as we do shift the original image, right, and then subtract the intensity from the given image without the shift. So this is without the shift, this is the shifted value. Okay, this will be pretty much constant if it is, you know, somewhere in the middle of a table or something. Okay, but if it's in a corner, as we discussed, then it will start to, every time we change, it will start to, so to give you a very simple explanation, let's say this is the corner of the window. Let's say we have the window over here. So let's pretend all of this is like black surface. Okay, and then over here is all white background. Okay, so if you take a look over here, if the window is over here, if we did I, X, Y, X plus U, Y plus B minus X of Y, and pretend UI is just 1 pixel. Okay, so meaning 1 pixel to the right, 1 pixel bottom. So as you can see, as we move it 1 pixel to the right, there will be more black area being counted, right? And as we move it down, same thing over here. So the difference will start to increase between white and black. If white is 255, black is 0. You'll see as we do the summation overall, this will, the value will increase. Okay, anyway, so that's the idea. Okay, so the question now is, we need to come up with some exact calculation. How do we do X plus U, Y plus V? Okay, so if you recall, we did the Taylor series in one of our previous lectures where we said if we have X plus delta X, Y plus delta Y, right? So the value of the function, just delta x, delta y away, can be approximated as f of xy plus delta x, f prime of xy with respect to x, or let me just call it fx, plus delta y with respect to y, right? And same way we can go delta x squared over 2, second derivative in the y, and so on. Okay, so so this part over here could be obtained through Taylor series expansion. So if you just focus on just this part, okay. So u could be delta x, v could be delta y. Okay, so this would be the original value of the pixel plus whatever the shift is, and what is this over here? The derivative in the x direction. Okay, this is derivative in the y direction. How do we obtain derivative in the x direction? What type of filter do we apply? Right? So this was the Sobel filter, the gradient in the x direction. And same way for the y, we can do, correct? So anyway, as you can see, if we applied the x filter, y gradient filter to the original image, then we can easily calculate this part over here, the first part over here, by simply the first order approximation. Okay, so that's what the author is doing. So let's go to the next slide. Okay, so anyway, instead of delta x that I was putting over here, the author is leaving it as u and v. Okay, so f of x basically means derivative in x direction, and f of y derivative in the y direction, correct? So this will be the first derivative expansion. Same way if we wanted to go to the second one, this is the standard Taylor series formula. We wanted to go to the third one, and so on. So this is basically the Taylor series of expansion around x plus u, y plus v. Okay. So in our case, okay, we'll just forget the second and third derivatives. We'll just focus on just the first order approximation. So our equation simply becomes u, derivative with respect to x, derivative with respect to y of the original function or the original image. So then, okay, so now let's focus on computing this part. Okay, so we do the Taylor series expansion for this part. Okay, which is, as you can see, this part. Everybody agrees? So think of ix over here is the derivative with respect to x, derivative with respect to y. U and v are like the shift in x, shift in y, like the delta x, delta y. Okay, so once we express this, expand this in Taylor series. Okay, now does this get canceled out?
Yes.
Right. So now do uix plus viy square, whole square. So wouldn't this become u square ix square, v square iy square, and then the cross 2 times u, v, ix, iy. Right? We can put this in matrix form. Okay, as ix square, ixy, ixy. And you can verify this. Okay, see, if I did a row by column, wouldn't this be u ix square row by column plus v xiy? Correct?
Yes.
Row by column. Then next one, row by column will be Ix, Iy, plus V Iy squared, correct? And I haven't done another UV over there. So this will be okay, this is 1 by 2. 2 by, yeah, I should put them side by side. So this will be, okay, this, then this, U, Ix, Iy, and V, Y squared. And then UV. So anyway, if we further now 1 by 2, 2 by 1, as you can see, this will become U square Ix squared. So U square Ix squared plus V UV Ixy. Anyway, and then once we go to this one, this will become UV Ixy, so which will make it 2 UV Ixy, and finally V square IV. So anyway, you can easily verify that in matrix form, this is exactly the same as this. Okay. Okay. So now. Okay, now on the next page, what the author will do is call this some matrix M. So if I go to the next page. Okay, so as you can see, whatever we had in the middle, so that over here, or it's right over here. So M is basically this Ix squared. So once again, what is Ix? What is Iy? Ix is the derivative of the image in x direction. And Iy is, so basically once again we'll apply the Sobel kernel to the image. To obtain Ix, we'll apply the Sobel kernel for the y direction to obtain Iy. And then we can easily compute this particular matrix over here. So okay, so let me skip that part. We already went over it. Okay. Okay, so here's okay, if it is a corner, as we discussed, if we plot Ix versus Iy, then there will be a high variation in Ix, high variation in Iy. If it is really flat surface and moving the window doesn't do anything, then the data for Ix, Iy will be very clustered together. If it is like a edge, right edge, then our Ix, Iy variation will, with respect to x and y, will look something like this. Okay. So if we take a look at now, try to understand this. So intuitively this makes sense. For a corner, the data will be distributed like this, right? So from eigenvalues point of view, or eigenvectors point of view, okay, as you can see, what will be the magnitude of the eigenvector in this direction compared to this one? Won't this have a higher magnitude?
Yes, due to the data.
Right? Same way over here. So here, the two magnitudes for the eigenvectors will be very small. Okay. Here, only one will be high, the other will not be high. If it is a corner, then if we compute the eigenvalues of Ix and Iy, the M matrix, then they will be high in both directions. That's the idea behind Harris corner detector. So okay, so anyway, so lambda 1, lambda 2 are the eigenvalues. As you can see, both the eigenvalue in this direction, eigenvalue. So in this case, it will produce two eigenvalues which are large. And why we have two eigenvalues? Let me go back over here. See, if you take a look at this matrix, this is basically a 2 by 2 matrix. Okay, even though X, the I image could be a 100 by 100 image. Okay, once we apply the Sobel filter, it will still be a 100 by 100 image. Everybody agrees? If we don't count the first, I mean, don't worry about the first row and the last row and the, right? Okay, so how will it be a 2 by 2 matrix then? Because if you take a look, this is summation over the entire window. So XY within that window, so this could be 10 by 10 window or 5 by, but anyway, so what I'm trying to say is there's a summation over here. So in the end, this is basically a single number. This is a single number, this is a single number. So this is really a 2 by 2 matrix. If you have a 2 by 2 matrix, how many eigenvalues will it produce? 2. 2. How many eigenvectors? 2. Okay. So that's why if we take after computing this summation, now if we take a look at, okay, but before I go, let me clarify this further one more time. Okay. Suppose the original image is 100 by 100, right? Whatever that image is, like this, whatever. Okay. Now, once we do Ix by applying the Sobel filter, like -1, -2, -1. Okay, it will still be 100 by 100, right? If we did a zero padding, even though it will become 98 by 98, but let's pad it with zeros. So as you can see, Ix will be still 100 by 100. Iy will be 100 by 100, correct? Okay, so once we compute it, we'll store it, both the filtered X image, filtered Y image, okay? Then, now we pick a window. Let's pretend the window happens to be somewhere here. Okay, so this is our 10 by 10 window. So now try to understand this. What is this going to do? So pretend in this window, X varies from 40 to 50. Okay, Y varies from 30 to 40. So this is the Y variation. Okay, so as we multiply this by window, what's the value of the window outside of this range? See, outside of this range, the value is 0. Because the window function is like this, it's 1 in a particular range, it's 0 outside. So as we are multiplying this with the filtered image, only between 40, 50, 30, 40, this matrix will exist, otherwise it will not exist. Okay, so what I'm trying to say is this summation will essentially become the value of the Ix squared summed between X of 40 and 50 and Y of 30 and 40. So even though originally it was 100 by 100, only in this window we are basically summing. That's what I'm trying to say. Okay. Anyway, and now we'll still get a 2 by 2. And now looking at the eigenvalues of this, if both eigenvalues are large, it will tell us it's a corner. If one of the eigenvalues is large, other is not, then what will it tell us? It's an edge.
Direction either.
Okay, and if both are small, then
Solid in the middle.
solid in the middle. Exactly. That's the idea.
Question.
Yes.
What if the eigenvalues are not real numbers?
For a positive, for images, usually the eigenvalues, because we don't have any negative values over there, everything is positive, eigenvalues come out to be real. Okay. But in practice, you are right, they can be negative. Okay. Sorry, they can be imaginary, not negative. Okay. Even if they come out to be imaginary, we can take a look at the magnitude of the number. So, so even if lambda 1 came out, let's say 3 plus I2, the magnitude is 3 squared plus 2 squared. So that magnitude will tell us, you know, whether it's a large value or a small value. Okay, so anyway, let me, where were we? Yeah, so we were looking at this part over here, right? So if both lambda 1, lambda 2 turn out to be large, it's corner, otherwise it's edge. If both are small, then it's a flat surface, as you guys, anyway, that's just the, okay, so now to put, because we have two eigenvalues over here, right? Lambda 1, lambda 2. So we need still some kind of a threshold. Like, what's our criteria? You know, right now we just said, if both are large, it's a corner. If both are small, it's not a corner. But how do we know what is large? And so that we can distinguish. So the Harris corner algorithm defines a term called R as the response, which is determinant of M minus K times, K is some parameter, trace of M. Trace of M are the diagonal, sum of the diagonal values. So the definition of a determinant is, and by the way, it doesn't matter, let's say you were given a 3 by 3 matrix. Okay, how many eigenvalues will it give you? 3. Lambda 1, lambda 2, lambda 3. So the determinant of this matrix is always a product of the eigenvalues, and you can verify it yourself. Okay. For example, let's see, this is the example I gave you, right? What's the determinant over here? 3. And what was lambda 1, if you recall?
3 is 1.
So lambda 1 times lambda 2 is 3, right? So it's same as the determinant. Okay, so anyway, determinant M is always product of the eigenvalues. Trace basically are the diagonals, which in this case is defined to be lambda, the sum of the, right? Okay, so basically in the Harris corner detector, after we have computed the 2 by 2 matrix, the M matrix, which was 2 by 2, we compute the two eigenvalues, lambda 1, lambda 2. Okay, then we'll compute the response by multiplying the 2 minus k. K is like some parameter over here that we can pick. Okay, and then we'll put a threshold on the R. So if it is above a certain value, it's a corner. Okay, so here's the typical value of k, 0.04 to 0.06. Anyway, let me skip that part. It's pretty straightforward. Here's the final algorithm. So let's examine this algorithm. Okay, so the overall algorithm, as you can see, will go in this these 4 or 5 steps. Compute x and y derivatives of the image. So Ix, as we had discussed, is the derivative in the x by applying a Sobel kernel. Okay, what does star mean over here? No? Convolution. Okay, I is the not the identity, but the original image in the author's terminology. So what is Gx of sigma? So this is, okay, why do they have sigma? Okay, it's yeah, but it should be Sobel, not a Gaussian. Anyway, I can double check that by taking a look at the OpenCV implementation. So this is basically a Sobel. Whether we need Gaussian before the Sobel or not, it could be they're trying to eliminate the noise, the high frequency noise. So this could be Gaussian first, then Sobel. Okay, so Sobel in the x direction, once again, -1, -2, -1, 0, 0, 1, 2, 1, right? And the y direction very similarly. Okay, so I can double check whether they do apply Gaussian before doing the Sobel, but anyway, the point is this will be the derivative in the x, derivative in the y, then compute products or derivatives at every pixel. Okay, so we'll do ix times ix, iy in the cross. Okay. Okay, so anyway. Okay, just 2 more minutes, so hopefully. Okay, so once we have computed the ixx, iyy, ixy, right? Sums of products and derivatives at each pixel. So, so basically we are computing sx2, sxy, and sy2. Okay, oh, I see what they did. This G sigma 1 is basically the Gaussian being used as a window. Anyway, let me double check on that one. Most likely that's the one because we do the convolution. This will basically give us the sum of x2, sum of y2, sum of y2, right? Then we assemble this, because if you recall in the M matrix, there was a summation involved. So basically, now we are summing to produce this M matrix over here. Then we will compute the eigenvalues, lambda 1, lambda 2 of this Hessian over here, which is basically the derivative in the x squared, derivative in the y squared, and the cross derivatives, right? Then we compute the response, just as we discussed, so that we can put some kind of a numerical value to whether it's a corner or not. So we do the determinant of h minus trace of h. And lastly, we'll pick some threshold, for example, 1.2 or 0.8 or whatever. If it is above that, it's a corner. If it is less than, it's not a corner. Okay. So I'll provide an OpenCV code for you guys to play with so that you can see how do we detect the corners. Okay. All right, so we'll continue from this point.